Atomically engineered catalysis, stabilizing single-atom catalysts via oxide nanoglue architectures. Single-atom catalysts, SACs, represent the ultimate limit of metal dispersion in heterogeneous catalysis, offering maximal atomic efficiency and unique catalytic properties. However, their practical implementation is hindered by limited thermal and chemical stability due to sintering under reaction conditions. Recent advances demonstrate a novel nanoglue strategy, in which atomically dispersed metal species are confined on oxide nanoclusters anchored to high surface area supports. This approach enables both stabilization and retention of catalytic activity. This video presents an overview of this strategy, focusing on cerium oxide nanoglue systems for platinum-based SACs, including synthesis, structural characterization, stability, and catalytic performance. Heterogeneous catalysis underpins numerous industrial processes, including petroleum refining, polymer synthesis, and emissions control. Conventional catalysts typically consist of metal nanoparticles dispersed on oxide supports such as silica or alumina. Because catalytic activity occurs at surface-exposed atoms, reducing particle size enhances efficiency. In this context, SACs, where metal species are isolated at the atomic level, represent the theoretical maximum in atom utilization. Despite their advantages, SACs face intrinsic instability. Isolated metal atoms are thermodynamically prone to migration and aggregation into clusters or nanoparticles, particularly under high temperature or reducing conditions. This sintering process reduces active site density and diminishes catalytic performance. Traditional stabilization strategies, such as strong metal support interactions, often compromise catalytic activity by limiting accessibility of active sites. Nanoglue strategy for stabilizing single-atom catalysts. To address the stability-activity trade-off, a three-component catalyst design has emerged. A high surface area support, for example, silica, alumina, dispersed oxide nanoclusters, nanoglue, atomically dispersed metal species, M, localized on these clusters. In this architecture, oxide nanoclusters act as anchoring domains that strongly bind metal atoms while preserving their mobility within confined regions, enabling catalytic turnover without aggregation. Cerium oxide is particularly effective as a nanoglue material due to its redox flexibility and high density of defect sites, cerium 3+, which serve as anchoring centers. Importantly, platinum exhibits a significantly stronger affinity for cerium oxides than for silica, ensuring the preferential localization of PT atoms on nanoglue islands. Synthesis of cerium oxide, Nanoglue-Supported SACs. The synthesis involves a scalable aqueous phase method based on strong electrostatic adsorption. Negatively charged SiO2 surfaces are functionalized with positively charged cerium hydroxide species. Thermal treatment, calcination, converts these species into isolated cerium oxide nanoclusters, approximately 2 nanometers. A subsequent adsorption step introduces PT precursors, for example, hexachloroplatinate, which selectively binds to cerium oxide due to electrostatic and chemical affinity. Control of platinum loading ensures that, on average, each nanocluster hosts a single platinum atom. This selective deposition is critical to achieving high dispersion and avoiding nucleation on the inert silica surface. Structural and electronic characterization. Advanced characterization techniques confirm the structure and dispersion of the catalysts. HAADFSTEM imaging reveals uniformly distributed cerium oxide nanoclusters on mesoporous SiO2. X-ray diffraction, XRD, indicates ultra-small crystalline domains with fluorite structure and lattice distortion. Raman spectroscopy identifies oxygen vacancies and structural defects. X-ray photoelectron spectroscopy, XPS, shows a high fraction of Ce3+ species, corresponding to enhanced anchoring capacity. X-ray absorption spectroscopy, XANES/EXAFS, confirms atomically dispersed platinum species with no platinum-platinum coordination. Infrared spectroscopy, DRIFTS, demonstrates characteristic CO adsorption on isolated cationic PT sites. Collectively, these data establish that platinum atoms are site-isolated and strongly coordinated to CeOx nanoclusters. Stability under reaction conditions. A defining advantage of the nanoglue strategy is its exceptional stability under harsh catalytic environments. Platinum atoms confined to carium oxide islands remain atomically dispersed under both oxidizing and reducing atmospheres. No significant sintering occurs even after prolonged exposure to hydrogen at temperatures up to 600 degrees Celsius. In contrast, platinum atoms supported directly on SiO2 or bulk CEO2 readily aggregate under similar conditions. This stability arises from the strong platinum-cerium oxide interaction combined with spatial confinement, which allows atomic mobility within islands but prevents long-range diffusion and coalescence. Catalytic performance. The cerium oxide-supported platinum single-atom catalyst exhibits enhanced catalytic activity, particularly in carbon monoxide oxidation, a key reaction in emissions control. The improved performance is attributed to high dispersion and accessibility of PT active sites, synergistic interactions between platinum and the redox-active cerium oxide support, stabilization of catalytically relevant oxidation states. These features collectively enable efficient catalytic turnover while maintaining structural integrity. Advantages and limitations. The nanoglue approach provides several advantages: maximized utilization of precious metals, enhanced thermal and chemical stability, and tunable catalytic properties via nanocluster composition. However, some limitations remain. Catalytic behavior is influenced by the chemistry of the nanoglue, potentially limiting generality. Partial oxidation of metal atoms under certain conditions may reduce activity. Precise control of nanocluster size and distribution is required for scalability. Outlook and future perspectives. The nanoglue concept represents a significant advance in the design of robust SACs. By integrating strong anchoring with spatial confinement, it overcomes key barriers to practical application. Future research directions include extending the approach to other metal oxide combinations, for example, titanium and iron oxides, increasing metal loading while maintaining atomic dispersion, exploring applications in electrocatalysis, hydrogen production, and selective organic transformations. With continued development, nanoglue-stabilized SACs are poised to bridge the gap between fundamental catalysis research and industrial implementation. In conclusion, the development of oxide nanoglue architectures provides a powerful and generalizable strategy for stabilizing single-atom catalysts. By confining isolated metal atoms on defect-rich oxide nanoclusters, this approach achieves both high catalytic activity and exceptional stability. These advances mark an important step toward the widespread adoption of SACs in industrial catalysis, enabling more efficient and sustainable use of precious metals.